Okay, let's consider the case of a book sliding down an incline. So it is moving down, and let's say it is speeding up down. So it also has an acceleration down the incline. Okay, we want to try and find out what the forces are, or analyze the forces to figure out that acceleration. Okay, so first let's identify forces. I'm going to draw a circle around my book. That's the thing I'm analyzing. What's interacting with it? Well, first, I have gravity interacting with it. Okay, I see a contact with the table, and that is doing two things. One is there's a normal force pushing outward on the book, keeping it from falling into the table. And then there's also, at that interface, there's also a frictional force. As it slides down, that frictional force is keeping it from, or wanting to inhibit its motion downward. Okay, so if this was if this surface was made of sandpaper or rubber, and the booklet had a rubber cover on it, then the frictional force would be quite large, and maybe it wouldn't accelerate downward or even move downward. It'd be able to hold it up. So that frictional force is pointing up. I don't see any other contacts around it, so I know these are the only three forces interacting with my my book. So now I'm going to translate that to a free body diagram. I've got a dot representing my object of interest, the object I've identified, and I'm going to draw a coordinate system that's most convenient for this problem. Now the motion is down the incline, so that makes sense that I should have an axis down the incline and then one perpendicular to it. I'm going to call down the incline my positive x, okay, because it's moving downward, and so that makes sense. My acceleration would be positive, my velocity would be positive. I could have done the other way, but I just have to keep my signs consistent. I'm going to go and choose out of the incline my y direction. And I'm careful to say out of the incline because it is not up, it is perpendicular to the incline. Okay, now I've got to get these three forces on that diagram there, that free body diagram. So, one I know is gravity, and gravity always, always, always points straight down. So I'm going to draw gravity down like this, labeled F sub little g. Okay. And before I do the other two, I want to break this into its components along my coordinate system. In fact, I'm going to need to do that before I can figure out how big are these. Okay, so I'm going to write the x component, or the y component, like that, so I can see those are the same length as projection onto the y-axis is the same length. So this is going to be f g y, and x is going to be that way, f g x. Okay, so I've got those that force decomposed on its axis. Every time you have a vector that's not on the axis, you want to decompose it to vectors on the axis, its components. Alright, now that I have the length of those two components, I can more confidently draw these ones. Okay, first of all, is this book accelerating in or out? No. It's constrained to move along the interface, so there's no acceleration, not even any motion at all, but most importantly, no acceleration in and out of the plane, which means there should be no acceleration along my y-axis, which means there should be no net force, which means the normal force should be equal to this y component of gravity. So I can draw that to be the same length as that one. So my normal force is equal to that one, indicating I know there's no acceleration in that direction. Okay, the book is accelerating downward, which means there is a net force down. Sorry, I should have been more careful. Down the incline. Okay, there's an acceleration down the incline, which means there's a net force down the incline, which means the gravitational force down the incline must be bigger than the resistive frictional force up the incline. So I have to draw a small vector there and label that frictional force. Okay. So looking now at this picture, I can see that there is a net force down. So I need to redraw that. It's a teeny net force. Okay, that's F net, and it is only in the x direction, causing this acceleration down the ramp. So that is now a complete free body diagram where I have labeled all the forces, decomposing any forces that aren't on the axis to their components on the axis, and being careful to make sure the relative lengths were accurate to indicate any known acceleration, or if I know their lengths, then I can find an acceleration, determine an acceleration from the known values here.